All right, let's dive into something that's literally all around us, but you probably never see it. We're going to talk about the invisible blueprint that powers so much of our digital lives. We're talking about graphs.
I mean, have you ever stopped to wonder, how in the world does Google Maps do that? How does it instantly figure out the absolute best route, weaving through traffic and construction? Or, maybe a little creepier, how does a social network know to suggest someone you met once at a party 5 years ago? Well, the secret behind all of this is a powerful yet really elegant concept in computer science called the graph. And no, I'm not talking about the X and Y axis charts you had to draw in high school math. In the world of code, a graph is all about connections. So let's break down what that really means.
Okay, so Section 1. What are graphs? The blueprint of networks. Before we can get to the fancy route-finding stuff, we've got to start with the absolute basics. What exactly is a graph from a computer's point of view?
At its heart, it's actually incredibly simple. A graph is just a collection of dots and lines. That's it. In computer science, we call the dots vertices, or sometimes nodes, and the lines connecting them are called edges. The easiest way to picture this is a map, right? The cities are your vertices, and the roads between them, those are the edges. Simple as that. Now, here's where it gets really interesting, especially if you're into coding. This bit of Python you see here, this is the blueprint. Think of this class as the set of instructions we give the computer. The init method just sets up an empty container for our cities. Then we have these little tools, these functions, like add vertex to plop a new city on our map, and add edge to draw a road connecting two of them. This is the foundation for everything else we're about to do.
So, let's move on to exploring a graph, traversing the network with BFS. Okay, so we've built our graph in code. We have our map of cities and roads. The next logical question is, how do we get around? How can we tell a computer to systematically visit every single spot in this network? One of the most fundamental ways to do this is an algorithm called breadth-first search, or BFS for short. The best analogy I've ever heard is to imagine dropping a pebble into a calm pond. BFS is like the ripples spreading out. You start at one point, you visit all its immediate neighbors. That's the first ripple. Then you visit all of their neighbors, the second ripple. You just keep going out level by level. It's a super orderly way to explore.
And this right here, this is the code that makes those ripples happen. You'll notice two really important things. First, there's a visited set. That's just a little checklist to make sure we don't visit the same place twice and get stuck in a loop. But the real workhorse is the queue. A queue is just like a line at the grocery store. First one in is the first one out. By using a queue, we make sure we visit everybody in the first ripple before we even start on the second ripple. It's what guarantees that level-by-level exploration.
And boom, here's the result. Let's say we start our search at vertex number 1. The code would first visit all of its direct neighbors. Based on this output, that would be nodes 2, 3, 4, 7, and 5. Only after it's visited all of those does it move to the next level, which is where it finally finds node 9. This output proves that layer-by-layer method works exactly as planned.
All right, next section, finding the shortest path. This is where we get back to that Google Maps magic. Because let's be honest, just visiting every node is cool, but what we usually want is to find the quickest, most efficient way to get from point A to point B.
Exactly. In the real world, not all roads are created equal, right? A 10-mile highway is way faster than 10 miles of winding country roads. We can represent this in our graph by adding a weight or a cost to our edges. So the highway might have a low weight and the country road a high one. So the question becomes, how do we find the path with the lowest total weight?
And the classic genius answer to that question is Dijkstra's algorithm. The way it works is actually pretty intuitive. It's like a super cautious explorer. It starts where you are, and it always takes the next step to the closest unvisited place. And every time it takes a step, it updates its math, asking itself, wait, did I just find an even faster way to get over there? It keeps doing this until it's found the absolute best route to everywhere.
And the code really shows this logic beautifully. You see how it creates that distance dictionary? It starts by setting the distance to every single node to infinity. That's the computer's way of saying, I have no idea how to get there yet. But then, as the algorithm runs, it starts replacing those infinities with actual numbers, actual costs, constantly updating its knowledge until it has a perfect map of the fastest routes.
And here's what that perfect map looks like. If we start at node 1, the algorithm crunches the numbers and tells us the shortest possible distance to get to every other node.
Getting to node 2 costs 1 unit, but getting all the way to node 9 costs 3 units. This is precisely what your phone is doing, just with a graph that has millions of nodes instead of just a handful.
So, we've covered getting around a network that's already built. But what if you're the one building it? What if you have to connect a whole bunch of locations, say houses in a new neighborhood, with internet cable? How do you connect everyone while using the least amount of cable possible?
That problem is solved by finding something called a minimum spanning tree, or an MST. An MST has 3 simple but crucial rules. Number 1, it has to connect or span every single point. Nobody gets left out. Number 2, it has to have the minimum possible total cost. You add up the weights of all the edges you use, and that number has to be as low as it can possibly be. And number 3, it has to be a tree, which is a fancy way of saying no loops or redundant connections.
And you might think, okay, that's a neat little puzzle, but the real-world applications for this are just massive. You're talking about the actual design of telecommunication networks, laying fiber optic cable across a country. It's used in designing efficient circuits on a microchip. It's even used in computer vision and handwriting recognition. It's everywhere.
So once you start seeing the world through the lens of graphs, you can't unsee it. From your social network, to the flow of packages in a delivery system, to the very fabric of the internet itself, it's all just graphs. So the next time your phone finds that perfect shortcut, you'll know the elegant code that's working behind the scenes. The real question I want to leave you with is this: what complex network in your world are you going to see as a graph now?